In this project, I will demonstrate how to generate PWM signal with different duty cycle and frequencies. Open ESK Studio, then click on File icon, then select New, then select NSS C++, then select NSS RA project. After naming your project, click on Next button. Here select FPB RA0E1 board from this drop-down menu. Then click on Next button. Here select None option, then click on Next button. Here select Executable and No Autos option, then click on Next button. Here select Bare Metal Minimal and click on Finish button. By default, IDE will open FSV configuration file. Click on Stack tab, then click on New. Then click on timer, then select PWM stack. First we need to add slave channel for master timer stack. Now click on add slave channel button, then click on new button. Now click on slave channel, then open properties window. We need to configure output pin for this slave channel. For operation mode select custom and for pin select P100. Now scroll up and expand P1. Now select P100. For GPIO mode select disable option. Now if we check, error from P100 is removed. Now click on stack tab, then click on G timer 0 stack, then open its properties. Now expand general tab. Now for period unit option select microseconds and for period select 50. We don't need to change anything further. Click on generate project content, then click on proceed button. Now click on C++ button to open C++ perspective, then expand src folder and open hall-entry.c file. Now in Project Explorer window, expand Developer Assistant tab, then drag and drop PWM open function call in hall-entry.c file. Now declare FSP error variable and use assert function to make sure PWM open function call was successful. Now from Developer Assistant tab, drag and drop PWM start function call in hall-entry.c file. Now use assert function to make sure PWM start function call was successful. Now click on your project name, then click on this hammer icon to build your project. After a successful build, right click on your project name, then select debug as, then select NSS GDB hardware debugging. Now click on switch button to switch to debug perspective. In debug perspective, click on this resume button twice. I have connected P100 with logic analyzer to analyze PWM signal in detail. Now I will analyze the signal generated by P100. P100 is generating a 20 kHz frequency signal with 50% duty cycle. Let me show you how we are getting 20 kHz signal with 50% duty cycle. If you open property for G timer stack, you can observe that period unit we have selected microsecond and period unit is 50. If you open calculator and divide 1 million by 50, we will get 20,000. That's why we are getting a 20 kHz frequency signal. Why we are getting 50% of the duty cycle? For that you can open properties for the slave PWM channel. Now expand output option. Here the last option PWM duty cycle percentage. By default 50 is entered here. You can click on 50 then change it to desired value. I am changing it to 75. Then again click on generate project content. Now click on proceed button. Then click on this hammer icon to build the updated project. As the debug session is already active, IDE will ask you to restart the debugging session. Click on yes button to restart the debugging session. Now click on this resume button, then open Logic Analyzer software. And now you can start recording the PWM signal. Here you can observe that the duty cycle has been changed to 75 as we enter in slave channel properties window. Now I will demonstrate how to change duty cycle with the help of Developer Assistant tab. First we need to declare timer information variable. Now from Developer Assistant tab, drag and drop PWM info get function call in hall-entry.c file. Now we need to define a variable to get current period counts. We can get that from timer info variable. Now use assert function to make sure PWM info get function call was successful. For second argument, we need to give the address of timer info variable. According to FSP documentation, we can use this formula to get duty cycle counts. Now we need to define example desired duty cycle percentage variable here. and then define example max percentage variable here. For maximum value we can define 100. Now from developer assistant tab, drag and drop PWM duty cycle set function call in hall-entry.c file. Use assert function to make sure duty cycle set function call was successful. For third argument we can change it to 1. Then click on your project name, then click on this hammer icon to build your project. Now right click on your project name, then select debug as, then select Genesis GDB hardware debugging. Now click on switch button to switch to debug perspective. Here click on resume button twice. Now open logic analyzer software. Then record PWM signal for some time. Now if I zoom in the PWM signal, we can observe that the duty cycle have been changed to 5% as we defined in the code. I have edited the source code to dynamically change the duty cycle after some blocking delay. Now change the desired duty cycle percentage variable to uint8t variable. Now declare while one loop here, then move the code inside while one loop. At the loop end we can add 5 to desired duty cycle percentage variable and then introduce 1 millisecond delay using RBSP software delay. We don't need to change anything further. Now click on your project name, then click on this hammer icon to build your project. Now you can press this debug icon to start debugging session. Now click on resume button twice, then open logic analyzer software. Now I will record PWM signal for a short duration. Now we can analyze the captured PWM signal. Now if I zoom out to 1 millisecond time duration, here we can observe that after every 1 millisecond duty cycle percentage will increase by 5. Every column here represents 1 millisecond duration. Within that duration duty cycle will remain same. After that it will be incremented by 5. Now I will demonstrate how to change frequency of PWM signal. Now we can comment out the while one loop here. For multi-line command, first you need to select multiple lines. Then you need to press Ctrl plus forward slash to comment out multiple lines at once. Now from developer assistant tab, drag and drop PWM period set function call in hall-entry.c file. Now use assert function to make sure PWM period set function call was successful. Now open FSP configuration file and click on this information icon to open FSP documentation. In FSP documentation, we can study the example related to period set function call. Now we can get timer frequency in Hertz by using info.clock frequency. Then we can calculate period count by using the following formula. Now we can define PWM example desired period in millisecond and PWM example millisecond per second. For first variable we can define 1000 and for second variable we can select the value of 20. Now click on your project name, then click on this hammer icon to build your project. After the build is complete, you can click on this debug icon to start the debugging session. In debug perspective, click on this resume button twice. Now open logic analyzer software and capture the PWM signal for some time. Now you can observe that frequency have been changed from 20 kHz to 1 kHz.